Hi everyone, in this session I'll talk to you about character encoding. Before diving into it, you need to understand two concepts: encoding and decoding. I'll use a little story to help you easily grasp what encoding and decoding mean. Once upon a time, there is a group of pirates found a treasure chest full of gold. But they had a problem. They needed to hide the location of the treasure, in case someone tried to steal it. So their captain, Blackbeard, came up with a clever plan to use a secret code. Blackbeard drew a map with the treasure's location, but instead of writing plain directions like sail north for 10 miles, then east for 5 miles, he encoded it into a secret message. He made the message follow this rule. The letters A, B, C, and D represent north, south, east, and west, respectively. And the numbers were replaced with symbols. For example, exclamation mark means 1, @ stands for 2, hashtag is the meaning of 3, etc. These rules saved as a dictionary. So then, the real instructions, sail north 10 miles, then east 5 miles, came like this. Blackbeard gave this encoded message to his first mate, and gave the dictionary to one of his sailors, Alex. Blackbeard told to guard them carefully. One day, the pirates decided to dig up the treasure. So now, the first mate owned the message, while the sailor had the dictionary. Neither of them can get the treasure with the information they each hold. So to obtain the treasure, they decided to cooperate. Using the dictionary in the sailor's hands, they decoded the information in the first mate's position, one word at a time. At last, they got the message. Sail north for 10 miles, then east for 5 miles. So, based on this information, they successfully dug up the treasure. Okay, back to our lesson. When a computer reads and stores data, it also needs encoding and decoding. For example, if you want to store the word hello in the computer will refer to a dictionary. This dictionary is technically called a character set. Essentially, this character set provides a mapping, where each letter is represented by a specific number. For instance, we could use 104 to represent the letter H, 101 for the letter E, and 108 for L, and 111 for O. Of course, we could define other rules, and this process is encoding. Now, let me mention why we need to represent letters with specific numbers. Computers only recognize two numbers, 0 and 1. This means that ultimately, data must be stored in the computer in binary form. However, binary numbers are hard for humans to read and remember, so we first convert letters to decimal numbers, and then the computer internally converts these decimal numbers to binary numbers for storage on a hard drive. One day, when you want to retrieve this data, you'll need to decode it. Naturally, decoding is done according to the same character set, where you map each number back to the letter it represents. This process is called decoding. Here's a key point. As I mentioned earlier, there isn't just one character set. In other words, there are multiple ways to encode and decode data. Why are there so many ways to encode and decode? Let's start from beginning. Computers were invented in the USA, right? For Americans, letters, numbers, and punctuation marks were enough for daily use. So the first character encoding system designed was called ASCII, American Standard Code for Information Interchange. It included uppercase letters, lowercase letters, numbers, and some symbols. It used 7 bits of binary, which means there were a total of 128 characters. For early American use, these 122 mappings were sufficient for daily use. We can open the ASCII code website and take a look. From 0 to 127. So there are a total of 128 characters, right? For example, the word hello in our earlier example is represented using ASCII code. You can see here H is 104, E 101, L 108, and O 111. Later, when computers spread to Europe, the limitations of ASCII became apparent. For example, these characters couldn't represent. So they extended the ASCII table using 8-bit encoding. As we know, 2 to the power of 8 is 256. So the extended ASCII table could represent a total of 256 characters. Let's return to the ASCII code website. Scroll down and look at the extended ASCII table. As computers continued to spread to other regions of the world, such as China, a new problem arose. For Chinese, 256 characters or even 2,560 characters weren't enough to represent such a vast array of Chinese characters. Then what could be done? So the Chinese developed a character encoding system called GB2312, which included 6,763 commonly used Chinese characters and 682 symbols. Later, with continuous improvement and further expansion, the GPK standard was created, including more than 20,000 Chinese characters. It not only supported simplified Chinese, but also traditional Chinese. So now think about it. This is just for Chinese, right? What about other regions in the world? There are thousands of languages. Each would need its own character encoding, leading to more and more chaos. Eventually, an ultimate boss emerged, UTF-8. This encoding system is incredibly powerful and can encompass nearly all the world's languages, characters, and symbols. Here are 2 important principles I need to emphasize. Principle 1. When storing data, always use an appropriate character encoding. Otherwise, storage may fail, resulting in data loss. This is because if the wrong encoding is used, the computer won't recognize the content you are trying to store. Principle 2. Use the same encoding method for storage and retrieval. Otherwise, the data may appear, but it will be corrupted or garbled. It's like using the wrong dictionary to translate, leading to errors in the decoded content. Next, let's move to VS Code and demonstrate these 2 principles. First, we'll create a simple text file. In it, let's write I love you in different languages. Start with English. And then let's use Google Translate to find translations in other languages. For example, let's pick Hindi. Next, okay, Japanese. Finally, Chinese. After writing these, I'll copy this file and name it decode.txt for use in demonstrating the second principle later. Now, what encoding should use to save it? Look at the bottom right corner of VS Code. Do you see UTF-8? What does it mean? It means that when VS Code saves the file, it doesn't ask you. It defaults to use UTF-8 for saving. This is the encoding process. Now close the file and reopen it. Why can we still see the content? Because when decoding, it also uses UTF-8. Let me show you what happens when we don't follow the first principle. Click this button. You'll see two options. Reopen with encoding. This is for decoding. Save with encoding. This is for encoding. Now, let's select Save with encoding. A list of encoding options will appear. Let's pick ISO 8859-1, which is one implementation of the extended ASCII character set. Click it. What happens next? Nothing? It seems like nothing has changed, right? Well, let me tell you, actually this file is already corrupted. Except for English characters, no other text has been saved to the disk properly. Let's verify this. Go to the folder and open the file with double-click. Do you see all the non-English characters have turned into question marks? But when didn't VS Code reflect the changes? This happens because VS Code uses a caching mechanism. On the surface, it still looks the same, but if you close and reopen the file, you'll see that it's indeed corrupted. Except for the English text, everything else is now a series of question marks. And here's the bad news. Once you see question marks, there is no way to recover the data. The question marks mean that the encoding process has failed, and the original data was not written to the disk. Let's test this. Try saving the file again with UTF-8 encoding and reopening it. What do you see? It's still question marks, isn't it? This demonstrates that once the encoding process fails and the data is lost, there is no way to fix it. The data is permanently gone. Then let's move on to principle 2. Let's look at the second principle with an example. Open the decode file we just saved earlier. Thankfully, we saved it before. Click on UTF-8. This time, select the first option, Reopen with encoding. Let's choose Chinese GPK encoding. What happens? Except for the English text, everything else has turned into gibberish. Why? This time, encoding was successful, which means the data has been successfully stored on the disk. However, because the wrong decoding method was chosen, the translation during reading went wrong. But if you click UTF-8, then reopen with encoding, and choose the encoding method used during storage, for example, UTF-8, you'll see everything is restored. These are all for text file. Then how about HTML file? Now, let's take it a step further. If it's an HTML file, the same principles apply. After writing your code, it's handed over to the browser, which reads it and renders it for the user. Here comes the question. How does the browser decode the file? The browser needs to know the encoding method used for storage. But looking at your code, there's no line that explicitly tells the browser what encoding method you use. Here's a commonly observed behavior. Most browsers will default to UTF-8 encoding for decoding if you don't specify any encoding method. If the storage encoding was indeed UTF-8, the browser can seamlessly display the content. But if a different encoding was used during storage and the browser defaults to use UTF-8 for decoding, what do you think will happen? Correct, you'll end up with gibberish. To prevent this, it's best practice to use a line of code to explicitly tell the browser which encoding method was used. You do this by adding a meta tag to the head section with the chassis attribute specifying the encoding. For instance, here we'd write UTF-8. Let's test this. Copy the text we used earlier into the body of this HTML file. Save the file. Open it with Live Server. As you can see, everything displays properly. Now, let's change the chassis attribute to GPK, which tells the browser to use GBK for decoding. However, we saved the file using UTF-8 encoding. What do you think will happen when we save and refresh the browser? Theoretically, gibberish should appear, right? Let's test this. Save the file, refresh the browser. Wait, something's not right. Everything still displays properly. Why? Because Live Server saved us. It noticed the file was encoded with UTF-8 but declared GBK in the HTML. So it quietly informed the browser, hey, don't trust this guy, he's lying. Ignore the GBK declaration. This file should be decoded with UTF-8. The browser thankfully cooperated. If you bypass Live Server and open the file directly by double-clicking it, guess what? Gibberish appears. After discussing so much, you might feel a bit overwhelmed. How should we handle this in practice? Let's open today's notes, where I've summarized everything for you. When writing code, always use UTF-8 encoding. This is the most reliable method. When writing HTML, to prevent potential browser issues, always include a meta tag with the chassis attribute in the head section and specify the encoding UTF-8. All the other things we talked about are just for your understanding. Okay, let's recap. Data storage involves encoding. Data retrieval involves decoding. Encoding and decoding must follow a specific set of rules, referred to as a character set. There are many common character sets. Here are a few examples for your reference. Principles. Principle 1. When storing data, choose an appropriate character encoding based on the import content. Nowadays, we mostly use UTF-8. Principle 2. The method used during encoding must be the same as the method used during decoding. Otherwise, gibberish will result. That concludes this session. After class, feel free to visit some well-known websites and check their chassis values using view page source to see if they are all using UTF-8. Thank you for watching. If you found this video helpful, please like and subscribe to my channel. See you in the next video.